Okay, electrochemistry. Oxidation reduction reactions involve energy changes. Because these reactions involve electronic transfer, the net release or net absorption of energy can occur in the form of electrical energy rather than as heat. This property allows for a great many practical applications of redox reactions, the branch of chemistry that deals with electricity-related applications of oxidation reduction reactions is called electrochemistry. So this chapter is basically about how we apply redox chemistry to practical application. Like, what's the point of having redox chemistry? How do we use it?
The controlled flow of electrons making possible laptops and phones and cars and pacemakers. Batteries, just like everything else in life, is just chemistry raised to the power of awesome. The kind of chemistry that happens inside of a battery is called electrochemistry because it involves reactions that produce or consume free electrons. Specifically, they are oxidation or redox reactions, the ones where electrons are exchanged.
Okay. So the main topic for this section is electrochemical cells. Redox reactions involve the transfer of electrons from the oxidized to the reduced substance. If these two substances are in contact, a transfer of energy as heat happens as well. So here's an example. We've got a zinc strip inside of a copper sulfate solution. So what's going to happen is you have down here, you've got copper ions, and up here, obviously, you have solid zinc. So these two are going to react in a redox reaction, and so that's going to involve a transfer of heat as well, which you see by the increase in temperature. So the zinc strip is going to lose electrons to the copper 2 ions that are in solution. The copper 2 electrons will accept the electrons from the solid zinc, and they will fall out of solution as copper atoms, which you see down here. As the electrons are transferred, energy is released as heat, as indicated by the rise in temperature. This is because they're in direct contact. However, if we separate the substances that electron transfer comes with the transfer of electricity instead of heat. One way of separating them is with a porous barrier. The porous barrier prevents the metal atoms of one half reaction from mixing with the metal atoms of the other, but it does allow a transfer of the anion. The ions in the two solutions can move through the porous barrier, so electrons can be transferred from one side to the other using the conducting wire. The current moves in a circuit, so the movement of the electrons is balanced by the movement of negative ions in solution. So if zinc is oxidized and copper is reduced, then that means that the electrons are going to go from here to here. And then that means that the sulfate ions are going to go from here to here. So if you look at figure 19-7, actually that would be, this is from the old book. It is on page 618, it's figure 1.2, 618, figure 1.2. Change that. Yeah. Okay, so we separate the copper. Oh, that's what, okay. So yeah, basically figure 1.1 on 617, the one from the previous slide that I showed you with when they're in direct contact, if you separate them with a porous barrier and then you connect them with a wire. So let me go ahead and change this really quick. What is it? 1.1, 1.2, okay. Okay, so the zinc strip is in an aqueous solution of zinc sulfate and the copper is in copper sulfate. So they have the same anion. Both solutions are called electrolytes. Remember, an electrolyte is a conductor used to establish electrical contact with non-metallic parts of a circuit like an electrolyte. So the zinc and the copper strips are the electrodes. Now, if we take just half of it, so this half is called a half cell. It's a single electrode immersed in a solution of its ions. In this example, the zinc strip in the zinc sulfate is called the anode. The anode is where oxidation takes place. Very easy way to remember this is that anode and oxidation both start with a vowel. Anode oxidation. The copper half cell is the copper strip in the copper sulfate. That's called the cathode. The cathode is where reduction takes place. Again, the two start with a consonant. So easy way to remember: anode oxidation, cathode reduction. When we write the notation for a half cell, because the copper half cell is the cathode and it's being reduced, we write it in the method, or in the, I don't know what the word is, but we write it in the same way that the half reaction would be. If we're writing the half reaction for reduction, we would write Cu plus 2 plus 2E goes to form Cu. That's the reduction half reaction, but we don't include the electrons. So we write the ion with a vertical line and then the reduced substance. The zinc half cell is written the same way because when you write half reactions, you write them always as reduction reactions. There's a reason for this because when we look at standard electrode potential, everything's written as a potential to be reduced. Why they decided reduction, I don't know. There's a reason for it, or somebody just flipped a coin, but the half cells are written as reduction reactions. The two half cells together make what's called the electrochemical cell. This is a system of electrodes and electrolytes in which either chemical reactions produce electrical energy or an electric current produces chemical change. So there's going to be two kinds of electrochemical cells that we're going to look at in this chapter. One of them is voltaic, one of them is electrolytic. So the difference basically is voltaic cells take chemical energy and it turns into electrical energy. These are batteries. And electrochemical cells use electrical energy to produce chemical energy. These are like when you have rechargeable batteries, and the batteries that are voltaic cells, they run out of chemical energy. You put them in your little chargers and you plug it into the wall, and then it becomes an electrolytic cell. But we'll get into that later. An electrochemical cell can be represented by the following notation. You write the anode, vertical line, cathode. So for our zinc copper example, because zinc is being oxidized and copper is being reduced, you write it Zn with a vertical line and Cu. That would represent the whole electrochemical cell. Again, anode first, cathode second. Just remember to put them in alphabetical order, then you don't have to worry about it. And like I said, there are two types of electrochemical cells. There are voltaic cells and electrolytic cells. Voltaic cells are also called galvanic. These are the batteries.